May I begin by thanking the organisers for giving me the privilege to present this public lecture. In this talk, I aim to cover the entire history of European mathematics, illustrating it with some of the 1,500 mathematical postage stamps in my collection. As you'll see, it's remarkable how much mathematics has been celebrated in this way. I always begin with this set of 10 stamps entitled "The 10 Mathematical Formulas That Changed the Face of the Earth." Although issued by Nicaragua, it includes mainly European mathematics, such as the Pythagorean formula, Archimedes' law of moments, and Newton's law of gravitation, and ending up with Einstein's equation E = mc squared. You'll see some of these again later. My talk is chronological, and we'll begin with some ancient geometry, the circular arrangements of stones at Stonehenge in England, and the linear ones at Carnac in France. We don't know their exact purpose, but it seems that they marked astronomical events, such as sunrise on Midsummer Day. But European mathematics is usually taken to begin with ancient Greece. From about 600 BC, it flourished throughout the Eastern Mediterranean, where the Greeks developed deductive logical reasoning and proof, the hallmark of their work, especially in geometry. Our earliest Greek mathematician, around 600 BC, was Thales of Miletus in the top row, who predicted a solar eclipse and showed how to cause electricity in feathers by rubbing with a stone. In geometry, he supposedly proved that a circle is bisected by any diameter and that the base angles of an isosceles triangle are equal. Below is Pythagoras of Samos. Another semi-legendary figure, he formed a school in Crotona, now in Italy, to further the study of mathematics and science. Supposedly believing that all is number, the Pythagoreans emphasized the four so-called mathematical arts of arithmetic, geometry, astronomy, and music, later known as the quadrivium. Several stamps feature the well-known Pythagorean theorem for right-angled triangles, that the areas of the two smaller squares add up to the area of the large one. Or in algebraic form, which the Greeks didn't use, a squared plus b squared equals c squared. We don't know who first proved this, but its connection with right-angled triangles was already known years earlier in Mesopotamia. The scene then moved to Athens, which became the most important intellectual center in Greece, numbering among its scholars Plato and Aristotle. In 387 BC, the philosopher Plato, top right, founded a school in the suburb of Athens named Academy. And Plato's Academy became the focal point for mathematical study. It's said that over the entrance appeared the inscription, "Let no one ignorant of geometry enter here." And in Raphael's fresco, The School of Athens, below left, you can see Plato and Aristotle on the steps of the Academy. Convinced that mathematical training was essential for his ideal citizens, Plato taught the quadrivium subjects of arithmetic, geometry, astronomy, and music, and described the 5 regular or Platonic solids shown here, the cube, tetrahedron, and so on. While his pupil Aristotle formalized deductive reasoning, discussing such logical syllogisms as all men are mortal, Socrates is a man, therefore Socrates is mortal. Around 300 BC, following the military successes of Alexander the Great, mathematical activity moved to Alexandria in the Egyptian part of the Greek world. The first important mathematician there was Euclid, mainly remembered for his Elements, the most widely read and influential mathematical work of all time. A model of deductive reasoning, it included geometry, arithmetic, and number theory, building them up from initial axioms to a whole hierarchy of results that he derived in a logical and systematic order. One of the greatest mathematicians of all time was Archimedes from Syracuse, now in Sicily. Around 250 BC, he investigated spheres and cylinders, listed the 13 Archimedean or semi-regular solids, and found estimates for pi such as 22/7. In mechanics, he found the law of moments for balance and the Archimedean screw for raising water, both shown on the right. In statics, he stated Archimedes' principle on the weight of an object immersed in water and used it to test the purity of a gold crown. On discovering this, he supposedly jumped out of his bath and ran naked down the street shouting, "Eureka, I found it." We now turn from Greece to the Islamic world from about AD 750 onwards. United by their new religion and with Baghdad lying on the east-west trade routes, their scholars developed Greek writings from the West and Hindu writings from India. Some of our present terminology dates from this period. The word algorithm, a step-by-step procedure for solving a problem, comes from Al-Khwarizmi on the right, whose influential book on arithmetic introduced the Indian decimal place value system to the Islamic world. He also wrote another book whose title gave us the word algebra. The Islamic world gradually developed, and by the year 1000, it had spread across the top of Africa and up into southern Europe through Spain and Italy. Cordoba became the scientific capital of Europe, while Islamic decorative art spread throughout southern Spain and Portugal, with the geometrical arches in Cordoba's mosque on the left and the tilings in Granada's Alhambra on the right. Also in Cordoba lived the geometer and astronomer Al-Zarqali, who constructed astrolabes. These are suspended brass discs with a rotating bar and a scale on the rim. To measure a star or planet's altitude, you viewed it along the bar and read the result from the scale. Meanwhile, the period from 500 to 1000 became known as the European Dark Ages. Much of the legacy from the ancient world was forgotten, and the level of culture was low. Revival of interest began with the French scholar Gerbert of Aurillac on the left, who trained in Catalonia and introduced the Hindu-Arabic numerals to Christian Europe. A major figure in the church, he was crowned Pope in 999. Next is the Catalan mystic Ramon Lull, who believed that all knowledge could be obtained by combining God's divine attributes, such as power, wisdom, and goodness. His combinatorial ideas spread through Europe, later influencing such figures as Mersenne and Leibniz. A surprise here is Geoffrey Chaucer on the right, author of the Canterbury Tales. His learned treatise on the astrolabe was one of the earliest science books in the English language. The Hindu-Arabic numbers were also popularized by Leonardo of Pisa, or Fibonacci, in his Liber Abaci, Book of Calculation of 1202. This famous work contained many problems, such as his problem of the rabbits below, that leads to the Fibonacci sequence of numbers above, 1, 1, 2, 3, 5, 8, 13, and so on, where each successive number is the sum of the previous two. These numbers also arise in the arrangement of seeds in sunflowers and in pine cones on the left. The ratios of successive terms of the Fibonacci sequence approach a limit, the golden ratio, which is about 1.618. A rectangle with sides in this ratio is sometimes considered to have the most pleasing shape, not too thin or too fat. And as shown in the Swiss stamp below, if we remove a square from such a rectangle, we get another one. This stamp also features the logarithmic spiral, the related logarithmic spiral, seen in the Nautilus shell above. The Middle Ages Renaissance in learning was largely due to three things: the establishment of universities, the translation of Arabic texts into Latin, and the invention of printing. The first European university was in Bologna, founded in 1088, with Paris and Oxford following soon after. For hundreds of years, the curriculum was based on the Greek quadrivium, with arithmetic and geometry shown above on the right, and astronomy and music below. Gutenberg's invention of the printing press around 1440 enabled mathematical works to become widely available for the first time. At first, these were in Latin for the scholar, but gradually vernacular works in the language of the people appeared at prices accessible to all. As well as text in arithmetic and algebra and geometry, there were practical works on commercial mathematics. Among these vernacular works was Luca Pacioli's Summa in Italian, top right, a 600-page compilation of contemporary mathematics, which included the first account of double-entry bookkeeping. While in Germany, the commercial arithmetic by Adam Riese below was also very influential. Printing also led to standardizing mathematical notation. The symbols for plus and minus first appeared in a German arithmetic text of 1489, but those for times and divide didn't come till much later. It was around this time that painters learned how to give visual depth through geometrical perspective. The first of these was Brunelleschi, below left, who designed the dome of Florence Cathedral, and his friend Alberti, who presented mathematical rules for perspective and insisted that the first duty of a painter is to know geometry. Above, Piero della Francesca's well-known Madonna and Child with Saints shows perfect perspective. His books also included polyhedron woodcuts by his friend Leonardo da Vinci on the right, who warned, "Let no one who is not a mathematician read my work." Another celebrated artist was Albrecht Dürer, who learnt about perspective in Italy and introduced it into Germany. In the middle is his engraving of St. Jerome in his study, showing his use of perspective. And on the right is Melancholia, depicting several mathematical objects, such as a giant polyhedron, a sphere, and in the background, a 4x4 magic square. The Renaissance period also coincided with many great sea voyages and explorations. From Portugal, Vasco da Gama, top left, became the first European to sail around the tip of Africa and reach the west coast of India, while other famous explorers included Christopher Columbus in the middle and Ferdinand Magellan on the right. Such explorers needed accurate instruments for navigating at sea, such as the mariner's astrolabe shown below. And also below is Pedro Nunes, the leading figure in Portuguese nautical science and one of the first Europeans to apply mathematical techniques to cartography. As well as astrolabes, other navigational instruments included quadrants in the shape of a quarter circle or 90 degrees, sextants, a sixth of a circle or 60 degrees, and octants, an eighth or 45 degrees. To measure an object's altitude, you viewed it along the top edge of the instrument, and the position of a movable rod on the rim gave the reading. Earlier, Levi Ben Gerson had invented the popular cross staff on the right for measuring angles between celestial bodies. But to find the angle between the sun and the horizon, you had to look directly at the sun. The back staff shown below was a clever modification where you had your back to the sun. Trying to represent the spherical Earth on a flat surface led to new types of map projection for use by navigators. The best known of these was by Mercator, who first projected the globe outwards onto a vertical cylinder and then adjusted the scale so that lines of latitude and longitude appeared straight, as did fixed compass directions. And Mercator's projection is illustrated below. He was also the first person to use the word atlas for his book of maps in around 1590. The 16th century was also important for astronomy, which became completely transformed when Copernicus replaced earlier Earth-centered planetary systems by one with the sun at the center, and the Earth is just one of the planets in circular orbits around it. His book on the revolution of the heavenly spheres was published in 1543. But the Copernican system was controversial, bringing its supporters into conflict with the Church, which placed the Earth at the center of creation. Several Copernican supporters were arrested by the Inquisition or burnt alive for heresy. Before the invention of the telescope, the greatest observer of the heavens was the Danish astronomer Tycho Brahe. In his observatory of Uraniborg on the island of Havane, he designed instruments of unequaled accuracy and measured over 700 stars, discovering a new star or nova in the constellation of Cassiopeia. His colleague, Johannes Kepler, is remembered for his 3 laws of planetary motion. From Tycho's extensive observations, he was led to propose elliptical orbits for the planets, with the sun at one focus, and to claim that the line from the sun to a planet sweeps out equal areas in equal times. Kepler was fascinated by ellipses and introduced the word focus into mathematics. He also rotated curves around an axis and found the volumes of over 90 solids of revolution by summing thin disks, thereby foreshadowing the integral calculus of some years later. Another Copernican supporter was Galileo, whose dialogue concerning the 2 chief world systems preferred Copernicus to the Ptolemaic system. At his famous Inquisition trial in 1633, he was placed under house arrest and wasn't pardoned by the Church until 1995. Galileo made extensive use of the telescope, drawing our moon's surface and discovering the moons of Jupiter and Saturn. His mechanics book, Two New Sciences, discussed uniform and accelerated motion and explained why the path of any projectile must be a parabola. Meanwhile, mathematics was developing in the Low Countries of Belgium and the Netherlands. Simon Steveen, top left, wrote an important treatise on statics and a popular book that explained decimal fractions. Johann de Witt, in the middle, calculated annuity payments and wrote on mathematical curves, while Christian Huygens, below, studied probability in curves, such as the cycloid and catenary, expounded the wave theory of light, and invented the pendulum clock. But a major problem of the time, particularly for navigators and astronomers, was numerical calculation. And in 1614, John Napier of Edinburgh introduced his logarithms, which replaced lengthy multiplications and divisions by much easier additions and subtractions. And the back of the stamp gives further information about him and his logarithms. The idea soon led to practical instruments based on a logarithmic scale, such as the slide rule. Dating from about 1630, they were used for over 300 years until pocket calculators appeared around the 1970s. While here in Slovenia, the mathematician and physicist Vega published a celebrated compendium of logarithms as well as 7-figure and 10-figure tables that ran to many editions. He also calculated pi to 140 decimal places. We now move to 17th century France, and first to René Descartes. An ancient Greek problem had asked how a point can move in a specified way relative to certain fixed lines. And to answer this, Descartes named two lengths, x and y, and calculated every other length in terms of them, obtaining a quadratic equation, a quadratic expression, a conic, as the required path. In this way, he introduced algebraic methods into geometry, a movement that will continue for the next 100 years. But Descartes did not introduce the Cartesian coordinates that are named after him. Descartes' most famous work was his Discourse on Method, a treatise on universal science, which included his contributions to geometry. 300 years later, France celebrated this with the upper stamp on the right, but unfortunately got the title wrong, and the sur was later corrected to de on the stamp below. Also in France, living just outside Paris, Mersenne was a Mennonite friar who made major advances on the mathematics of music and of sound. But he's mainly remembered for the prime numbers that are 1 less than the power of 2, such as 3, 7, and 31. 51 of these so-called Mersenne primes have now been found, and the stamp on the left shows one of these. It was the largest prime number known in 2004 when the stamp was issued. On the right, Pierre de Fermat is mainly remembered for developing analytic geometry and number theory. In particular, he famously claimed to have proved Fermat's last theorem, that the equation x squared plus y squared equals z squared has no positive integer solutions when n is larger than 2. And this was eventually proved by Andrew Wiles in 1995, whose name appears on the red bar across the equal sign on the Czech stamp. And next is Pascal, who showed an early interest in mathematics. When only 16, he discovered his so-called hexagon theorem involving 6 points on a conic. One of the very first to investigate the theory of probability, he's also remembered for Pascal's principle in hydrodynamics, Pascal's triangle of binomial coefficients, shown here, and for designing an early machine operated by cogged wheels that could add and subtract. Moving now to England, Isaac Newton was born in 1642. At the University of Cambridge, he was appointed Lucasian Professor of Mathematics, a post later held by Stephen Hawking. Together with Leibniz, he explained the inverse relationship between the two branches of the calculus: differentiation, that's how fast things move, and integration, that's the study of areas. The story of Isaac Newton and the apple is well known. Seeing it fall, he realized that the gravitational force pulling it to Earth was the same as the force that keeps the moon orbiting the Earth and the Earth orbiting the sun. And he claimed that this motion was governed by a universal law of gravitation, the so-called inverse square law, where the force of attraction between two objects varies inversely as the square of the distance between them. In his Principia Mathematica of 1687, perhaps the greatest scientific work of all time, Newton used this law to explain Kepler's laws of elliptical planetary motion, and also to account for cometary orbits, the variation of tides, and much else besides. But the Principia wouldn't have appeared if Edmund Halley hadn't cajoled the reluctant Newton into developing his ideas on gravitation and paid for its publication. Halley, or more correctly Halley, is mainly remembered for the comet named after him. Observing it in 1682 and realizing that it was the same comet as one seen many times earlier, he predicted its return in 1758. The comet's appearance then, several years after his death, did much to vindicate Newton's ideas on gravitation. Newton justly claimed priority for the calculus, but it was Leibniz who developed it independently, who was the first to publish it. But Leibniz's calculus differed from Newton's, being based on geometry rather than on velocity and motion. Also, Leibniz's notation was more versatile than Newton's. His d for differentiation and his integral sign, which is still used today, being introduced within just 3 weeks of each other in 1675. The Bernoulli family included several distinguished Swiss mathematicians, but only one of them appears on a stamp. In his book on the art of conjecturing, Jacob Bernoulli proved his law of large numbers, shown below on the right. With his brother Johann, he was the first to develop Leibniz's calculus, introducing the word integral and applying calculus to such curves as cycloids and spirals. Leonhard Euler also grew up in Switzerland, but spent his working life at the scientific academies of St. Petersburg and Berlin. The most prolific mathematician of all time, he contributed to almost every branch of mathematics and physics, including number theory, the calculus, mechanics, astronomy, and optics. Euler introduced the notations E for exponential, I for the square root of -1, and capital sigma for summation. And he linked the exponential and trigonometric functions in his equation e to the I phi equals cos phi plus I sin phi, which you can see on the left of the red stamp. In 1735, he solved the Königsberg Bridges problem shown below. Can one cross all the 7 bridges of the city of Königsberg without visiting any bridge twice? But Euler never drew this graph, which is often attributed to him. He also discovered the polyhedron formula, vertices plus faces equals edges plus 2, which appears on 2 of these stamps. In the 1730s, there was a major controversy over the shape of the Earth. In his Principia Mathematica, Newton had predicted that the Earth's rotation causes flattening at the poles, so that the Earth is onion-shaped, while a rival theory of Descartes claimed that it's elongated, so lemon-shaped. To decide who was correct, 2 geodetic missions were sent to Peru and Lapland. The Peru mission on the left was led by de la Condamine with the Spanish cosmographer Jorge Juan, while the Lapland mission on the right was led by Pierre de Maupertuis. These 2 missions confirm Newton's view: the Earth is flattened at the poles. Returning now to France, Napoleon's rise to power led to important developments in mathematics. Napoleon himself was interested in the subject. There's even a Napoleon's theorem, and his friend, the geometer Gaspard Monge, shown on the right, showed how to project 3-dimensional objects onto a plane while investigating gun emplacements in a fortress. And this type of geometry became known as descriptive geometry. An important consequence of the French Revolution was the founding of Paris of the Ecole Polytechnique. Here the finest mathematicians of the day, Monge, Lagrange, Laplace, and Cauchy taught students who were destined to serve in both military and civilian capacities. Lagrange, on the left, wrote on mechanics, the theory of functions, and number theory, and proved that every positive integer can be written as the sum of 4 perfect squares. Next is Laplace, remembered for the Laplace transform of a function and for Laplace's equation in physics. His monumental 5-volume treatise on celestial mechanics earned him the title of the Newton of France. Shortly after the French Revolution, a commission was set up to standardize weights and measures and to introduce a metric system. You can see that on the right. Its chairman was Lagrange, and its members included Laplace and Monge. Work and analysis then continued with Cauchy, shown below. The calculus was still on shaky foundations, but Cauchy rescued it with his formal treatments of limits and continuity. He also developed complex analysis, and the stamp below includes his so-called integral formula. Meanwhile, in 1826, there was a major breakthrough in algebra when the Norwegian Niels Abel solved a long-standing problem while visiting France. Although general formulas existed for solving quadratic equations and also cubic and quartic equations, no such formula was known for equations of degree 5 or more. Abel proved that no such formula indeed can exist. Abel's work was continued by Évariste Galois, shown below, who explained in algebraic terms exactly which equations can be solved. Sadly, Galois had a short and turbulent life, being sent to jail for political activities and dying tragically in a duel at the age of 20, having sat up the previous night summarizing all his mathematical achievements for posterity. On the right, you can see the Irishman, William Rowan Hamilton, a child prodigy who mastered several languages at an early age, who discovered an error in Laplace's work while still a teenager, and who was appointed Astronomer Royal of Ireland while still a student. He made important advances in mechanics and geometrical optics, and while trying to generalize the complex numbers, discovered a non-commutative system, the quaternions. These involve 3 square roots of -1, I, j, and k, satisfying the equations shown below on the lower stamp. Meanwhile, in Germany, Carl Friedrich Gauss was working on many subjects, from complex numbers, the Gaussian number plane on the right, to statistics, the Gaussian distribution. One of the greatest mathematicians of all time, he discovered which regular polygons can be drawn by straight edge and compasses alone. These include triangles and pentagons, and also the 17-sided polygon shown below. The early 19th century also saw a major revolution in geometry by Gauss and others. Euclid's element starts with 5 postulates. 4 of them are straightforward, but the 5th differs in style, resembling a theorem that ought to be provable from the others. One version is the so-called parallel postulate. Given a line L and any point O not on it, there's a unique line through O parallel to L. For over 2,000 years, mathematicians were unable to deduce this from Euclid's other 4 postulates. And this is because there are non-Euclidean geometries which satisfy the first 4 postulates, but not the 5th. These geometries have infinitely many lines through O parallel to L, as shown in the middle. They were first discovered around 1830 by Nikolai Lobachevsky of Russia on the left and János Bolyai of Hungary. Other new geometrical objects from the 19th century included the Möbius strip, which has only one side and one edge. Such new geometries forced mathematicians to ask, which geometry corresponds to the world that we live in? Is it our usual Euclidean geometry, or might it be a non-Euclidean one? And in fact, the geometry that arose later in Einstein's theory of relativity was due to the German Bernhard Riemann, who's never appeared on the stamp. But here are some pictures of Einstein, including the middle one that looks as if he only just got up in the morning, with his famous equation E = mc squared relating energy and mass on the wallpaper behind him. Meanwhile, there were developments in Russia. On the left is Ostrogradsky, who worked in mathematical physics and discovered the so-called divergence theorem, which is often credited to Gauss. Below him is Lyapunov, who studied rotating liquids and the theory of probability, while in the middle is Chebyshev, who worked on orthogonal functions, Chebyshev's polynomials, probability, Chebyshev's inequality, and also prime numbers. Below him is Zhukovsky, who studied the flow of fluids around solid objects, such as the air moving around an aeroplane wing. And on the right is Sonia Kovalevsky, who made valuable contributions to mathematical analysis and to partial differential equations, and who won a coveted prize from the French Academy of Sciences for a wonderful memoir on the rotation of bodies. Meanwhile, in Eastern Europe, Bošković was interested in astronomy, trigonometry, and optics, and showed how to calculate a planet's orbit from just 3 observations of its position. On the right is Bernhard Bolzano, born in Prague, who formalized the idea of continuity before Cauchy, proving the so-called intermediate value theorem that the graph of a continued function takes on all values between its highest and lowest points. While the stamps below commemorate the founding of the Union of Czechoslovak Mathematicians and Physicists and the Romanian mathematics and the Romanian monthly magazine Gazeta Matematica. Regrettably, few women mathematicians have been featured on stamps, but here are 4. Above is Sophie Germain, whose pioneering work on prime numbers and Fermat's last theorem greatly impressed Gauss. She also made important contributions to the theory of elasticity. Below her is Maria Gaetana Agnesi, a child prodigy who could speak 7 languages by the age of 11. In 1748, she published an early book on the infinitesimal calculus, and a cubic curve, the so-called Witch of Agnesi, is named after her. We met Sonia Kovalevsky earlier, and here's another Russian stamp commemorating her. Barred by her gender from studying in Russia, she went to Heidelberg in Germany, attending lectures by Kirchhoff and Helmholtz, and later on became the first female professor in Stockholm. Meanwhile, Florence Nightingale, the lady with the lamp, was saving many lives through her sanitary improvements in Crimean war hospitals. But she was an accomplished statistician, and she collected and analyzed Crimean mortality data and displayed them using her polar diagrams, a forerunner of the pie chart, which is shown on this Italian stamp. So at last we've reached the 20th century, when several mathematicians created the subject as we now know it. And here's a brief selection. The range of David Hilbert on the left was immense, from Hilbert spaces and number theory to potential theory and the theory of gases. In 1900, his famous lecture at the International Congress of Mathematicians in Paris featured 23 mathematical problems that set the agenda for research over the coming century. In the middle is Henri Poincaré, who wrote on the still unsolved 3-body problem of determining the simultaneous motion of the sun, the earth, and the moon. A gifted popularizer of mathematics, he also developed algebraic topology, differential equations, celestial mechanics, and much else besides. And in England, Bertrand Russell was making fundamental contributions to mathematical logic, such as Russell's paradox. With A.N. Whitehead, he wrote his 3-volume Principia Mathematica on the foundations of mathematics, in which the equation 1 + 1 = 2 isn't proved until page 86. Two analysts who are featured on stamps are Constantine Karateodori from Greece and Stefan Banach from Poland on the left. Karateodori studied the theory of functions and the calculus of variations, while Banach helped to create modern functional analysis and to develop links between topology and algebra. And the term Banach space is named after him. In the middle is Elie Brahe, a geometer and topologist and the founder of intuitionism. He's remembered for results in topology and for his refusal to allow proofs by contradiction. And on the right is Wacław Sierpiński, also from Poland, who made outstanding contributions to set theory, point set topology, and number theory. The fractal pattern below, known as the Sierpiński triangle, is due to him. And talking of fractals, Mercator issued a set of stamps featuring these self-similar patterns that reproduce themselves forever when magnified or reduced. And above are von Koch's snowflake curve, which has infinite length but encloses a finite area, and Hilbert's space-filling curve. The Israeli stamp below features a Julia set. This is a fractal pattern that arises from iterating a quadratic formula. And there's also a commemorative sheet featuring the so-called Mandelbrot set. But if you prefer something more light-hearted, there are mathematical games and puzzles. Here are chess and Go on the left, noughts and crosses, sometimes called tic-tac-toe, and the tracing of mazes on the right. And in the middle is Rubik's Cube, whose faces can be rotated to yield over 10 to the 19 different patterns. The object is to restore the original colors. And in the early 1980s, when the craze was at its peak, over 100 million of these cubes were sold. Mathematics also finds its way into contemporary art. And above are examples by Delaunay, whose circles represent bright streetlights, the vertical parallel lines of Bridget Riley, and the startling patterns of so-called op art. While below are Mondrian's Broadway boogie woogie, representing the grid-light streets of New York, and the many symmetries in Vasarely's Vega chess, which was inspired by his interest in the fourth dimension. Mathematics continues to advance at an ever-increasing rate, and since 1897, international congresses have been held around the world where thousands of mathematicians gather to learn about the most recent developments in their subject. Several of these congresses have been commemorated on stamps. Those from Europe were, on the left, Moscow, 1966, and Helsinki, 1978. In the middle are earlier Polish and Bernoulli stamps for Warsaw, 1983, and Zurich, 1996. And then more recently, ICM stamps on the right for Berlin, 1998, and Madrid, 2006. As for these European congresses, only 2 stamps have been issued. One was for the second ECM, held in Budapest in 1996. And the other, of course, is the stamp that's recently been issued here for the Slovenian Congress 8 ECM. So before concluding, I'd like to end by showing you some stamps with no mathematical content whatsoever, but which have unusual mathematical shapes. We start with various triangular stamps, both equilateral and isosceles, and both ways up. And above is a single example of a scalene triangle. We can then proceed to other polygons, such as these exotic rhombuses, parallelograms, trapezia of various kinds, regular and non-regular pentagons, hexagons, and octagons, leading eventually to circular stamps, such as golf balls and soccer balls, ellipses, and a semicircle. And there's even a stamp from Tonga, shaped like a banana. So finally, as we cast our minds back over 4,000 years, we might choose to emulate Time magazine's Man of the Year by asking whether there's been a stamp that celebrates the greatest mathematician of all time. And fortunately, the answer is yes. Thank you very much for listening. And you can see most of these stamps again at the Congress's stamp exhibition or on the website shown below.